Hi, this is the video for my project proposal, generating random walks in a graph with pre-trained language models. The goal of the project is to generate graphs and ultimately generate knowledge graphs where the nodes in the graph are entities from a knowledge graph. To generate graphs, there are two ways to approach the generation. One is to generate the adjacency matrix directly, and the other is to generate each step in a random walk of the graph. So the first way is maybe more intuitive, but ultimately infeasible in graphs with a large number of nodes. So if you imagine that you're generating an adjacency matrix for a graph with n nodes, you'll get this adjacency matrix. And this has a space complexity of n squared, which is not too great if n reaches something like, let's say, 1 million nodes. So it scales poorly with the number of nodes and is computationally inefficient because in most graphs that we observe in the real world, most of the nodes are not fully connected to every other node, so this adjacency matrix is going to have a lot of zeros. So alternatively, we can generate each step of the graph in a random walk. So in this case, we would be only focusing on, in this matrix, only focusing on the entries where there is an edge between two nodes. And this scales much better and bypasses the zeros in the adjacency matrix problem. So the way that you would do this is you would sample from an actual graph some random path that you can take, and you would only focus on generating paths that look like this. So on the adjacency matrix, this may be something like this. So why generate graphs? Well, there are many potential downstream use cases for graph generation. For example, in text data, you could generate knowledge graphs from a paragraph of natural language text, and then use that as the input to maybe a graph encoder that will learn the representation of the graph input. And in that case, representing the text in the form of a graph, which makes the entities and the relationships between the entities explicit, may be a better form of representation than sequential text. The basis of this idea is from this paper, NetGAN, Generating Graphs via Random Walks. And the formulation in this paper is that learning the graph topology is equivalent to learning the distribution of biased random walks over the graph. And in words, what this means is that given a set of nodes in a graph, we want the model to be able to model which, if taking a random walk over the graph, which paths are plausible given the structure and characteristics of the original graph. So if the original graph exhibited this sort of path, our generator model should be able to return a path that looks similar to this, maybe this path. That is not necessarily a copy, a memorization of the paths in the original graph, but similar paths that are also plausible given the nodes and the edges. So to do this, they use a GAN setup where there's a generator and a discriminator, and the generator learns to generate random walks like this, and then the discriminator D learns to distinguish the generated paths from the paths sampled from the original graph. So for the discriminator, if we had paths in the original graph that looked like this, but the generator generated a path here that didn't exist, then the discriminator would know that this is not a plausible path in the original graph and steer the generator model towards not producing these. The advantage of the method proposed in this paper is that we're able to learn the graph topology by efficiently considering only plausible paths in the original graph. And the paper suggests that doing this, considering the random walks, which are sequences of nodes and edges, contributes to learning the correct topology. The downsides of this approach is that applying GAN to a generator with discrete output samples, which is the case in a generator that produces language output, is known to be a difficult problem, and it's for this same reason that GANs aren't as popular in, say, language models, and I'll describe this problem in the next slide. In a language generation setting, the generator G has discrete output samples. What this means is that when you sample an output from the generator G, which let's say is an RNN or an LSTM, to feed to the discriminator, that action is a non-differentiable operation because the function G in the case of language, these are switched. In the case of language, the generator function G is a combination of LSTM and argmax operations, and these are not differentiable. Whereas in the case of images, the generator function can be just a deconvolutional network that takes in a randomly sampled vector Z and then outputs a real valued image, generated image. So in the discrete output case, calculating the gradients for the generator function requires reinforcement learning, Gumbel softmax, or straight-through estimator to approximate the gradient. And I guess the problem is that even when using these methods, the performance is usually not up to par with simply using the standard sequence loss. So this is one issue with using GANs for generating language output. We looked at the pros and cons of NetGAN for generating graphs. A second, somewhat related method for generating graphs is Comet. It's similar in that it also doesn't deal with the adjacency matrix, but generates paths directly. But in this case, the model is only concerned with a single tuple in the graph, not an entire path. So if NetGAN was operating over paths given by a random walk, Comet only deals with single tuples that consist of two entities and a relation. However, the advantage of this model is that it fine-tunes a pre-trained language generator to the task of generating graphs. So there is a potential to transfer knowledge from a powerful pre-trained model like GPT-2. And the methodology is simple. For a given graph, for all tuples of the format SRO, where S is the subject, R is the relation, and O is the object, we train a function that takes in S and R and generates the tokens of O. So we're predicting from the subject and relation the object of the relation with respect to the subject. The pros of this model is that it can potentially transfer a lot of useful knowledge from the pre-trained model. If we're generating a knowledge graph, since the pre-trained model sees so much text, it seems likely that information relevant to the entities in the knowledge graph will have been seen by the pre-trained model. And the paper also suggests that based on their results, there is indeed meaningful knowledge transfer between the two tasks of language model pre-training and the graph relation prediction task in this model. Additionally, a model like GPT is already trained to generate natural language sequences well. If you've seen like any demo of GPT-2, you can see that it is very good at generating realistic sentences or even paragraphs. So if we can leverage this aspect of the model, it could be beneficial in generating realistic graph paths. However, unlike NetGAN, in this paper they only consider single tuples or triples. So the function they learn really only has one time step. If we look at this G as a generator function, it can only produce results for one time step where it's given one subject, one relation, and produces one object. While it is possible to create paths with only this function by treating each time step separately, this is not ideal because at each time step you have no memory of what you generated in the past. And this leads us to our proposal for the project. As we can see, NetGAN and Comet have sort of precisely complementary advantages and disadvantages. So as a starting point, my proposal is to use the two methods together. That is, I want to try applying a pre-trained language model like GPT-2 to generate random walks in a graph like in NetGAN. That is, the G function or the generator function in the GAN setup in NetGAN would become a pre-trained language model like GPT. And I'll explain below, but having the GAN setup is also possibly optional. We do have the option to train the random walk generator without using an adversarial discriminator. The key assumption here is that learning random walks is more informative than simply learning the single node edge node tuples as in Comet. And if this is true, we would be able to directly compare with Comet and see that learning these random walk paths is better than simply learning single tuples. Assuming that knowing about longer sequences, aka random walks or paths, in a knowledge graph is informative, the proposed method would have an advantage over Comet in that it can consider paths in the graph that are multiple steps long. So if Comet only considered these single time step tuples, such as pathétique is also known as opus 13, or it's equivalent to some music webpage, or it's notable for being a piano sonata. Knowing the longer path would allow us to know about longer sequences of reasoning such as this one that piano sonatas are a composition type. So for example, let's imagine our model is at this node and wants to generate the next edge in the path. So one of these two, or maybe other paths pointing to other nodes. It's reasonable to think that by knowing that we're currently referring to an entity, pathétique, which is known to be a piano sonata, it'll help us in the decision making in terms of choosing the path to this entity, which is composition type. Now, it's possible that this assumption is false, and having a knowledge of the upstream path does not help. But I think to know the exact answer, we would have to run the experiments and perform comparisons. Just to reiterate, using a NetGAN style path generation task with an LSTM or transformer would give the model this memory of the path from its past decisions. And if there is any kind of long-term dependency over multiple steps that can help the model to make path decisions downstream, the model would be able to learn it by modeling this memory. So if there's any kind of dependency over multiple steps like this, the recurrent memory may prove to be useful. You might have noticed that I've only mentioned the generator part of NetGAN. This is only the generator part. This is because the adversarial setup with the discriminator, potentially giving it gradients, is completely optional to this part of the model. So we can just train the generator like a language model too, to predict the sequence of path decisions, since we have the labels from the original graph. So this part could just work like a language model. And a discriminator may be harder to train because of the issue I mentioned before about discrete output samples. But a comparison experiment could be done to compare the two types of training methods. We can use public KVs to train and evaluate our models. Common sense KVs use freeform text to represent nodes, so they have orders of magnitude more nodes compared to structured conventional KVs like Freebase and WordNet. But Freebase and WordNet are also large, and so the popular datasets for link prediction are these smaller subsets. These subsets contain tens of thousands of entities, dozens to thousands of relations, and hundreds of thousands of tuples. To evaluate the graph generation models, we would evaluate the graph generation itself by measuring the various statistics of the produced graph and by also using human judgment. We can also measure the link prediction ability on KVs, and while this task is dominated by graph embedding methods, we don't need to worry about direct comparisons because in our case the link prediction is a byproduct of graph generation, whereas the graph embedding methods discriminatively classify links. To summarize, the proposal is to take a pre-trained language model like GPT-2, like in Comet, and apply it to a sequential task of generating random walks in a knowledge graph instead of a single triple, borrowing the idea of NetGAN. To train the sequence generator, we may or may not use the GAN setup and simply use a next step prediction task like in language models. Some potential improvements that may be possible are that we may be able to generate large knowledge graphs which the netgen cannot do as is. And we may be able to do better on KB completion than Comet does, which, while it's good at generating diverse and precise target phrases, is not so good at link prediction. This concludes the proposal presentation on a way to generate knowledge graphs. Some of the details may be a little rough, but I hope the presentation conveyed the general idea of the proposal. And thank you for your time.